Today's lesson is called Classifying Real Numbers. So as you can see in the diagram in front of you, we kind of have a hierarchy of all the number system broken down into subcategories. We're going to start out with the largest category of all, which is right at the top, the real number system and the real numbers. The symbol for the real numbers looks like a set of parallel lines that are completely vertical, and then you make an R out of those lines. This counts for all numbers. So real numbers are all of the numbers. If you look at real numbers as the biggest number system, we're going to split that real number system into two groups. A group called irrational numbers that you see on the left, and a group called rational numbers that you see on the right. Let's start with rational numbers, the one on the right. These numbers, it says all fractions and decimals that end or have a repeated pattern. So let's underline end and repeated pattern. The letter Q is sometimes used for rational numbers. It's not so important as we move forward, but it is good to know, and it will allow us to abbreviate later in some of our practice activities. So examples of rational numbers, you're going to see in the box that has been created within the word rational that ratio is boxed in, and that's because ratio is another word for fraction. Hopefully this will help you realize that ratios are in the rational number system part of this. So we can have fractions, like 1/3. We can have decimals that end, like negative 0.67. We could also have a number like square root of 16 because 16 is what we call a perfect square. There is a number times itself that will give you 16. That number is 4. So because I can simplify that to 4, that's also considered a rational number. Now remember, we can also have repeating decimals like, 0.1 repeating or 0.3 repeating as well. Underneath rational numbers, which includes all the decimals and fractions, we have the integers. The integers are represented by the letter Z, and these are going to be all your whole numbers and their opposites. So if we go down one more category to whole numbers are described as a slight upgrade from the natural numbers. So since we're using these things to kind of define them, why don't we go all the way down to the natural numbers and talk about those. So for the natural numbers, we're going to use the letter N, and we're going to call the natural numbers also known as the counting numbers. So we're going to put that underneath. And the natural, the counting numbers are the numbers that you learned how to naturally count with. And so you see that in the box there, how you naturally learn to count. So when you were learning to count, you started with 1, 2, and 3. And then we're going to do ... to show that that pattern goes on. So now when I try to describe what the whole numbers are, we're going to use W for whole numbers. You'll see the box on the left says it's a slight upgrade, which means we're just taking the natural numbers and adding 0. So the only new number that makes it the whole numbers is adding the number 0. Then it's just the counting numbers. So the natural numbers are the ones you learned to naturally count when you were little. If I add just 0, we have the whole numbers. Think of it as a very slight upgrade. And then we get to the integers, which if you remember, I said was described as the whole numbers and their opposites. So I'm going to write down the whole numbers, kind of in the middle here, 0, 1, 2, 3, ... But then the integers are going to add in their opposites. So what's the opposite of 1? It's -1. What's the opposite of 2? -2. And then we're going to do ... this way to show that the pattern goes both ways. So now you can see if we start at the smallest, we can describe ourselves by working our way up. Natural is what we learn to naturally count with. Whole numbers, you just add 0. Integers, you add the opposites. Rational numbers, you're adding in all the fractions and decimals. Okay? So when we split the original real numbers into two groups, rational numbers have all these subcategories that they can be broken down into. If we go back up to real numbers and look at the two options we had, we did rational first, so now let's talk about the irrational numbers. These are decimals that never end and have no repeating pattern. So think of these as kind of the mumbo jumbo numbers. They really kind of are a mess. All right, so irrational numbers are denoted with a capital letter I. And these are numbers like pi. Think about what you know about pi. It goes on forever, never repeats. Pi is a classic example of an irrational number. We're going to say square root 2. 2 is not a perfect square. There is no number times itself that will give you 2. So that means when you type square root of 2 in your calculator, which you can do right now, you're going to get a pretty ugly looking decimal that will go on forever, but it's never going to repeat. Any number that goes on forever and doesn't repeat like that is irrational, or you can think of it as the square root of a non-perfect square. And that can even include putting a negative out in front, negative 101. 101 is not a perfect square. So if we take the square root of that on the calculator, you will get that ugly decimal that goes on forever but never repeats. So these are all just examples of irrational numbers. So that kind of takes the whole number system and breaks it down into categories and subcategories. So for the exercises, let's look at the first one. It says, name all sets of numbers to which each number belongs. So we're going to list the sets. And down here, just for space, we can use our abbreviations. So in number 1, we have 6/3. First thing I want to do is notice that it's a fraction, but that fraction can be reduced. So 6/3 is just the same thing as 2. So if I look at that as the number 2, let's think about all the categories it fits into. Think smallest to biggest sometimes will help. So if I look at the counting numbers, is 2 a counting number? It is. So I'm going to put natural or counting number there. Now, if I'm a natural number, because of where I am in the hierarchy here, you can see that means I'm automatically also a whole number. I'm also an integer. That means I'm also rational. And that means I'm also a real number. So because of where that fit in the hierarchy and the categories, I know all of the parts that it belongs to. All right, let's look at number 2, negative 2.875. This is a decimal that is ending. It ends or terminates. So that means if I'm picking between rational and irrational, remember rational numbers are the ones that either end or have a repeating pattern. So that means that this is a rational number, so we're going to use Q for rational. But if I'm rational, you can see I'm also a real number. And we're just using our abbreviations here. Okay, number 3. The square root of 21. So the first way to think of this is this number a perfect square? Is there any number times itself that will give you 21? The answer is no. So if you think of this as the square root of a non-perfect square, then you automatically know it's irrational. If you're not sure about that, you can type it in your calculator and you'll see a number come up 4.5825 and it'll go on and on and on, but never repeat. So because of that, this means that this is irrational, but then also a real number. And if you want to put a little note here, this is a non-perfect square that you are taking the square root of, which is why we have a problem and why it's irrational. Okay, in number 4, we have 5.3 with this little bar over it. So remember what that little bar means. The bar means that we have a repeating decimal. A repeating decimal. So that qualifies then as a rational number. Remember, rational are the ones that end or repeat. Okay, so this one would be rational, so we'll use Q for the abbreviation, and then real numbers as well. So there's just a little example of questions you could be asked. You will have to take a number and be able to tell me what number system subsets these belong to. Now, the first way that we showed you was one way to organize the real number system. We want to show you another way to organize it. So here you're looking at a Venn diagram. The directions say place the letter of each value in its location in the real number system below. So we'll start with letter A. Letter A is 0. So if I think about 0, when I learned to count, I started with 1, 2, 3. That's the natural numbers. We added 0 in order to get the whole numbers. So I'm going to take the letter A that represents 0, and I'm going to put it in the whole numbers. But if you look at the way this picture is, that also tells you all the other subsets that this belongs to. If it's whole, you can see that circle's inside the integers. It's also inside the rational, and it's also inside the larger box. This box in general represents the real number system. So I'll be able to tell you that 0 is a whole number, an integer, rational, and real right away because of where I place this in the diagram. Okay, letter B, 36 over 12 can be simplified into 3. 3 would be a natural number. It's one of the lowest subsets, the numbers we learn to count with. So B is going to go inside natural and therefore would be considered whole, integer, rational, and real as well. In letter C, we have negative on the outside, square root of 36. So that means we're going to take the square root of 36. So what number times itself is 36? That's 6. And tack the negative on. So this is actually negative 6. You can also type that in your calculator. Negative 6. We didn't get any negatives until we got to the integers. If you remember, integers were the whole numbers and their opposites. So C is going to go here. And that tells me that negative 6 is an integer, it's rational, and it's real. For part D, we've got 7.5, or if it's easier for you to think of, that's the same as 7.5. So we have a fraction, which is a ratio. That means it's rational. We have a fraction, or you can think of it as a decimal that ends. So that means this is an example of a rational number. D will go in there. We know that 7.5 or 7.5 would be considered rational and real. So for this example, we didn't have any irrational numbers. If we go back to one of the ones that we had before, like pi, I would just put pi here in irrational. So now to finish the lesson, we wanted to share with you just another diagram that you can use to help you memorize and learn the real number system and the subsets. This picture is almost backwards of the original picture that we showed. So some people like to look at the big picture first, like all real numbers, and learn how they break down into smaller parts from there. That's how we started. When we look at this one's talking about the smallest you could start. So this is your smallest, and working up to your largest. And here you have actual funnels. So you can see like the natural numbers or counting numbers funnel into the whole. Remember, just by adding 0. Whole go into integers by adding the opposites. Integers go into rational by adding in fractions and decimals that end. You can see your rationals totally separated because those are the decimals that never repeat and don't end. And then the biggest bucket of all is the real number system. So in this last part of the lesson, I'd like you to answer the question, what do you think? How would negative 100, take the square root, be classified? So what I'd like you to do is pause the video and try to answer this question, and then resume the video to go over the answer with me. So when you tried this on your own, you should have typed in the square root of negative 100 on your calculator. If you're having trouble doing this, make sure you ask for help the next time you see your teacher. And when you do this, when you type in the square root of negative 100, you get an error message. It's going to say something about non-real answers, or some type of error message is going to show up. So the important thing to know here is star. Make sure this is an important point. You can't take the square root of a negative number. It's impossible. Think about this. A perfect square comes from taking a number and timesing it by itself. That means I'm either doing positive times positive, which is always going to be positive, or negative times negative, which is always going to be positive. There is no such thing as a negative number that is a perfect square. So you can classify these. There's a special classification called imaginary numbers. which sounds really silly, but that's what they're called. And you actually work with imaginary numbers as you get up into higher level math. So my job is just to mention it now so that you know they exist, and then you'll do more work with the imaginary part of the real number system later on. So in closure, why does learning about the real number system help us? So again, you're going to pause the video and try this question and then resume the video to check your answer. I'd like you to give an example of a real world situation where we would need fractions in order to measure some quantity. Explain why fractions would be needed in this situation. So at this point, please pause the video and try to come up with an example, and then you can resume the video to see an example of mine. Okay, so why does learning about the real number system help us? I want to talk about what it means in real life. Give an example of a real world situation where we would need fractions in order to measure some quantity. So think about something that you do in your everyday life that you would need a fraction for, and explain why you would need it. So my example is the following. I like to go to the bulk section of the grocery store and buy candy or different things. So my example would be buying pounds of candy at the bulk section of the grocery store. It says explain why fractions are needed. Maybe I don't want to buy a full pound of candy. And I would need it because I want to buy maybe a half pound, which means I need 0.5, which means I need fractions and decimals in order to measure that quantity in real life. And I'm sure there's many other examples that we could come up with. That's just one that if you'd like to write down as an example, maybe that'll get your brain going and thinking about some other situations where they would be needed. So that concludes our lesson on classifying real numbers.